Okay, last time we discussed about the DC load line concept. So DC load line. So DC load line is actually the operating characteristic of the circuit. So this is actually the operating characteristics of the circuit. So how do you find the Q point or the operating point? So Q point. So we have this device characteristic. So device characteristic means the transistor we select. So according to the selection, so we can easily get the data sheet of this particular transistor, and from this transistor we can basically find out the variation of this collector emitter junction voltage along with the collector current. So this is available in any data sheets of the transistor. So this kind of for different base current. So you can have this multiple curves representing this VCE, ICE variation. So this is the device characteristic. So this is actually the device characteristic. So device characteristics. So once you finalize the circuit, I mean the layout of the circuit, what would be the configuration of the circuit, you can easily evaluate the equation for the DC load line. So we discussed how to get this DC load line done. So first, so you have to simplify the circuit to get the DC equivalent circuit by replacing these all capacitors with open circuit element and inductors with short circuit elements. Because this capacitor and inductor behave as open circuit and short circuit elements when we apply a DC quantity. So this is basically analyzed, numerically analyzed in circuit analysis tool. But in here we can simply use that concept. So capacitor and inductor can be simply replaced with the open circuit and short circuit element, and you can simplify the circuit to the DC equivalent circuit. So you have to first obtain the DC equivalent circuit. So DC equivalent circuit. So once you get this DC equivalent circuit, by applying Kirchhoff voltage law for the output circuit, including the collector emitter junction. So if you apply the Kirchhoff voltage law for the output circuit, including this collector emitter junction voltage, and rearrange the terms and to get the expression for the collector current as a function of collector emitter junction voltage. So this is the load line or the DC load line for this given circuit. So this represent the VCE, IC characteristics of the circuit. You can just overlay this information on the device characteristic we obtained previously through the data sheet, and then depending on our requirement we can basically decide the Q point of the transistor or the operating point of the transistor. So we know that if it is a kind of an amplifier, it should be placed on the active region. And if we want to make this transistor as a switch, you have to toggle the operating point or the Q point between the saturation and cutoff. So according to our requirement, we can basically place the Q point on this DC load line. So once you fix the Q point of the transistor, so we can easily pick the values for the base current, values for the collector current, values for the collector empty junction voltage. Those are actually Q point parameters. So once you get it done, so you can simply select the IBQ, the Q point base current, and VCEQ, the Q point collector empty junction voltage, and ICQ. So these are the three quantities we can easily pick from the above analysis. So based on those parameters, we can basically find out what are the resistors we can place onto this circuit to operate or to push this transistor to behave in this given Q point. So this is basically done. Now you have kind of idea how do we manage this Q point, how do we get this DC load line, and based on the DC load line how we can place the Q point on the load line. So for this particular example, I need to explain few things now. So these blue lines basically represent the device characteristic of the given transistor, and this red line represent the DC load line of the transistor. So from this we can do a kind of a simple demonstration how this system works. So let's assume now I place the Q point here. So this is my Q point. So this based on the Q point, so we can basically identify these parameters. So for example, in this case, the base current at this Q point is 46 microamperes, and the corresponding collector current would be this, and this is the collector empty junction voltage. Okay. So then, assuming that this is the Q point, so how do we get this done? So let's think about it. So let's consider a very simple circuit. Okay, so we have a circuit like this. Okay. So let's assume this common emitter configuration, very simple common emitter configuration. Now through this RB, so this through this base resistance RB and RC, we can manage the Q point to place it here. So now if we just draw the base current, so this is the base current. So this is the time, and this is the IBQ. So this is your base. This is equals to IBQ. This is equals to 46 microamperes. So this is the base current. So let's think of, so if you want to have a kind of an amplifier built on this transistor, so it means whatever the input we basically feed through the input circuit can be amplified and get it out from the output circuit. So now we place the transistor to operate in the active region, and the external inputs are basically fed to the transistor after this biasing. Now this process is called a DC biasing. So we take the transistor, we select the transistor, and we select the circuit configuration, and based on the circuit configuration we draw the DC load line, which basically characterize the operating region of this particular circuit. And based on our requirement we select the Q point, which is now in active region, Now we are ready to amplify the external input. Now this circuit is basically biased to operate the transistor at this given point. So now this entire process is called DC biasing. So now we basically bias the transistor to operate at this particular Q point. So now we are feeding an external time varying signal and see whether it's amplified accordingly. So now what we can do is I'm basically injecting an external signal. So this is the external signal. Let's assume it's a kind of pure sinusoidal signal. So I'm generating a kind of a sinusoidal signal having a 5 microampere peak. So through a kind of an external current source. So I just plug an external current source to here. And through this external current source, I am basically generating a 5 microampere peak current. So it means this is like 5 micro. So this is like minus 5 micro. So if I apply this to the base, what happens to the base current? So, already it has a certain amount of DC value, which is equals to 46 microampere, and on top of that, I am adding another sinusoidal current, which has a peak of 5 micro. So then this would be like this. So this is the ultimate current appear in the base terminal. So this would be actually the peak here is like 46 plus 551 micro, and here the minimum would be like 41 micro. Now instead of having this flat DC current of 46 microampere, we have a kind of a sinusoidally varying signal having a peak of 51 micro and a minimum of 41 micro. So then the base current is basically oscillating between 51 and 41. So this is the current actually feed into the base once we consider the external input. So this is the external current. So this is the external current. So this is external current. So let's assume it basically comes through a kind of a microphone. So based on the tone we generated to the microphone, so it induces a kind of a sinusoidal waveform which has a magnitude of 5 microampere peak. So this is basically superimposed on top of this DC bias based current, which is 46 microampere, and it generate a kind of sinusoidal having a DC offset of 46 microamperes. Now the current waveform is basically oscillate around this 46 microampere, which is our bias base current, and it has a maximum of 51 micro and a minimum of 41 micro. So then this is the actual base current we apply. So this is the IB actual. Okay, so if you want to make it precise, like this is IB. So the instantaneous current variation at the base. So we have a current having an average of 46 and it's moved to 51, then drops to 41, 46, 51 like that. So then if we consider the base, so this is your output. So this is your base. Now it means, so like, yeah. So let's assume this is your base. Now this is 46. So this is like 51. This is actually 41. Okay. So then what, so this is the corresponding base current for 51. This is the corresponding base current for 41 micro. So then ideally this you can take this base current variation by projecting this base currents on top of the load line. So this is the 51 micro and this is 41 micro. So you can simply find the Q point based on this set of blue curves, and then you can project it on top of the DC load line. So this is your input signal. So the Q point is basically move from here, and so it's basically oscillate between these two ends. So then you can easily project it to the collector emitter junction voltage and collector current. So then ideally if you project it, so it's something like that. So here we have this kind of arrangement, and here also kind of this kind of arrangement. So this is the collector current variation and the collector emitter junction voltage variation. So if you draw it, so initially, so you have this kind of a DC current of 4.8 milliamperes with this fluctuation. So you have this kind of a collector current. So this is like 4.8 milliampere DC. On top of that, you have kind of a sinusoidally behaving signal. Similarly, if you draw the junction voltage VCE, so for the VC also same. So we have like 5.8 volt. On top of that, you have this kind of a voltage variation due to the external input we provide. So then see, by looking at this set, couple of figures, you can see like if you basically input a kind of a 5 microampere peak current to the base, so you basically ended up with a kind of a heavy current gain. So the simply your base current is like 46 micro and 4.8 is the base collector current. So you can easily get a current gain. So you have collector current of 4.6 milliamperes and base current of 46 microamperes. So roughly you have like thousands of thousand gain here. So then if you basically have a peak of 5 micro, so then it would reflect to here as a kind of a 0.5 milliamp. So it's a kind of a reasonably higher gain with respect to the base voltage or base current variation. So this is the basic operation of the amplifier. So you can basically draw the DC load line, and on top of that you can view project whatever the inputs and see. So now, for example, if you bias your transistor which is close to the saturation. So let's assume you are biasing your transistor close to the saturation. Let's keep like this. Yeah. So then if you add a kind of input on top of this Q point, So this Q point is more towards to the saturation. So if you apply a kind of a symmetric external signal, there may be a high chance of moving the Q point to the saturation because it's pretty much close to the saturation region. So then if your Q point moves to the saturation region, we know that your collector current is a kind of a fixed saturation current. What about your collector emitter junction voltage? So ideally it should simply stay at 0. So then, like here, see that if you move your Q point to the saturation, so you ended up with a kind of a saturation current here and 0 voltage here. So then what happens to the output? So your output is basically distorted. So your input signal is having a pure sinusoidal, but with that input signal and the Q point you place the transistor to operate on, so there may be high chance to move the Q point to the saturations once it comes to this block. So then what happens, you can't see a kind of amplification in the collector current. So it basically push it to the saturation current and maintain a kind that value during that part of the cycle. And you can't see any collector emitter junction voltage amplification also because it's basically suppressed to 0. And once you increase your base current, you can observe like your collector emitter junction voltage simply maintain at 0. So then what happens is due to this effects, you will get a kind of a clipped version at the output. So the clipped version at the output. So either it may be clipped at the positive cycle or maybe clipped at the negative cycle depending on the circuit condition. For this particular case, so your output collector current and output collector emitter voltage is basically clipped at their positive cycles. So clipped at the positive cycles. So then this is called a kind of a distortion of our output signal. So when you place your Q point close to the saturation, so there is a high probability of moving your Q point to the saturation along with the input signal you fed to the system. So with that, you will basically have a kind of a positively clipped IC or VCE, and ultimately we'll get a distorted amplified signal. So it's not properly amplified, perfectly amplified. It's a kind of a distorted version of this amplified signal. Similarly, if you place your Q point close to the cutoff, like in the second figure, so then with the external input you fed to the circuit, there may be a high chance of having this kind of a region. So yeah, your Q point is pushed into the cutoff. So in this case, your Q point is put into the cutoff. So Q is put into the cutoff. So with that cutoff, you know that your collector emitter junction voltage is basically push it to the supply voltage, and you can't see any amplification. So the output is basically saturated here and it's fixed at VCC, and you can't see any kind of amplification beyond that limit. So at the same time, your collector current it simply drops to 0 and you can't see a perfect amplification during this period as well. So then if you place your Q point which is close to the cutoff with the input signal, there may be a high probability to push that Q point to the cutoff during certain cycles or certain parts of the cycle. So with that, we will end up with a kind of a distorted output, either a collector current or the collector emitter junction voltage. So then there is a kind of conclusion we can make. So if you place your cue point more towards to the saturation or more towards to the cutoff, there may be a higher probability of moving the signal to either cutoff or saturation. So what we can simply do is, so we can place the cue point in the middle of the load line, in the middle of the load line. So then we basically have we can get a kind of a maximum swing between these two extremes. So if you place your cue point either close to saturation or cutoff, so you cannot have this maximum swing. So what we can simply do is we can place the cue point which is close to VCC by 2, VCC by 2, which is the middle of this entire span. So if you place your cue point close to VCC by 2, so you basically have a maximum span for the cutoff direction as well as the maximum span for the saturation direction. So then you can basically guarantee that your circuit is behave pretty much smoothly for a certain for a kind of a pure symmetric external inputs. So you can guarantee that it never uh, ended up with a distorted version because you place your cue point in the middle of the DC load line, having a maximum span to the positive or negative direction. So if you place your cutoff close to one of these extreme ends or saturation or cutoff, so then definitely with the external input, it basically clipped at either positive cycle or negative cycle. So your output is simply get distorted and you cannot observe a kind of a pure amplification then. So this is the simple operation of the transistor based on the cue point and based on the rest of the parameters. So you get a kind of understanding about this clipping process of this transistor. Then with the biasing of the transistor, you can manage that one. And if you place your cue point close to the middle of the load line, you can have basically have a maximum swing to the positive and negative directions, and you can be on more safe side when you are operating in active region. So these are some clues or some simple concepts, ideas about this biasing. So now I basically believe like you have kind of an idea about what is actually biasing and how we can do the biasing, and how do we get the DC load line, and based on the DC load line how we can select the cue point, and when we place the cue point, what happens to the cue point when we change the cue point by increasing input signal or changing the other parameters like resistance and supply voltage, what happens to the load line and the cue point. And with this variation of these cue points and load line, there may be a tendency of pushing the cue point to either saturation or cutoff. With that, so you will ended up with a kind of a distorted version of your input signal. So it's amplified, but it's not perfectly amplified. So there's a kind of amplification there, as well as there's a kind of a distortion of the output signal. So you can simply simulate it using a Proteus and see how this happens. You can place your cue point close to the cutoff for saturation by changing the resistance and see. Uh, so then you can have a kind of a clear understanding about how this clipping of the output or distortion of this output it's happened with the input signals and the cue point which we basically place the transistor to operate on. Yes. So then so in the slide set, you can find these mainly three types of biasing techniques. So the first is actually fixed bias or base bias. So this is fixed bias. So here the simple difference is So you can connect your base to the supply voltage through a resistor. So with that you can basically do this DC biasing. So this is the fixed bias scenario. So we have this base resistor, which is basically connected to the supply voltage. Through this RB, we can adjust the IB. For example, if we apply Kirchhoff voltage law, we can simply say that Kirchhoff voltage law. So this is supply voltage, VCC equals to the current into IB into RB plus VB. So I just apply the Kirchhoff voltage law for the input circuit, including base emitter junction. So once you apply this Kirchhoff voltage law, you can get this IB into RB plus VB equals VCC. So we know that this is actually this is 0.7, and you can select IB as you wish based on the operating point. So this is the supply voltage. So you can select it according to the data sheet. And these are known quantities. This is a known quantity. This is again a known. So you can select the IB as you wish. So you can easily get the value for RB from here. So you can basically calculate the RB. Similarly, you can apply Kirchhoff voltage law for the collector emitter junction. So Kirchhoff voltage law for this collector emitter junction. So then similarly you can show that IC RC plus VCE equals VCC. So this is a known for the biasing point. So this is again known. IC also known. You can easily calculate RC. Okay, so if you are given the RC values and supply voltages and IC collector current, you can easily calculate the other parameters as well. So then basically once you rearrange this expression, you can get the DC load line equation, and by placing this DC load line you can have this kind of a manipulation of the circuit parameters according to your requirement. So this is very simple mechanism. You can take the part of the voltage through this RB or the base resistor. So then you can basically make the base emitter junction forward bias through this RB resistor. So it's basically connected to a single external source and powered the base emitter junction as well as base collector junction. So through this RB, you can basically have this biasing. But the issue is like once you place this RB, you don't have a control there because with the supply voltage and the RB, so your base current is basically fixed. So there won't be any, like you cannot basically control the base current without changing the RB. So this is very simple biasing mechanism. So other than that, we have some more flexible and advanced ways of biasing. The second option would be like emitter bias. So the second would be like emitter bias. So with this emitter bias, so you have a kind of a resistor placed to the emitter terminal. So here, so you can see, so the same configuration is there as in the previous fixed bias scenario, but in addition to that, we can basically place emitter resistance. So what happens with this emitter resistance? So if we apply this Kirchhoff voltage law for this base emitter junction, BE, so what happens? So you have IBRBs here, and you have this base emitter junction voltage, VBE. So other than that, you have that IER term equals to VCC. So if I replace this IERE with 1 plus beta IB, so you know that this IE equals to IC plus IB, and IC can be replaced with beta times IB. So then your IE is actually equals to 1 plus beta times IB. So then from here you can find a base current which is equals to VCC minus VBE, which is a known quantity, equals to 0.7. And here in the downstairs you have RB plus 1 plus beta RE. So see, so this RE is actually placed to the emitter terminal. So if you check with the previous here, so this IB equals to VCC minus VBE divided by RB. So here we have a single resistor here, and once it comes to this emitter bias, we have two resistors here. So then we can have a kind of a 2 degree of freedom by changing RE and RB. We can basically manage the base current. In the previous fixed bias system, so we have a single degree of freedom. So once you change the RB, the entire system or the Q point will be changing. But now we can basically manage the RB either by changing, manage the base current, either by changing the RB or RE. And at the same time, see what happens. So this RE, if you apply the Kirchhoff voltage law, if you apply the Kirchhoff voltage law for the collector emitter junction, so then we can simply say that IC RC plus VCE plus IE RE equals VCC. So for the time being, let's assume this is pretty much equals to IC. So then what happens? IC equals 1 over RC plus RE into VCE plus VCC divided by RC plus RE. So this is the load line equation for this particular scenario. So, and at the same time, this is the output characteristics. So this is the output and this is the input. See that R is up in the both ends. So it means, so if you see some changes in the output circuit, it can basically reflect to the input circuit also through the RE, emitter resistance. So this RE acts as a kind of a feedback mechanism. So it's RE is act as a kind of a feedback mechanism between the output circuit and input circuit. So with that, you can basically manage the behaviors, uncommon behaviors appear in the output side by informing to the input side through this RE to adjust its Q point values. So for example, if due to a certain reason, if you change the collector current, so you can just pass that information to the input side to decrease the collector current. So that's why we have this RE in both input and output circuit through this feedback mechanism. built through the emitter resistance. We can basically manipulate or have a kind of a common control between input and output. So this is a bit advanced mechanism compared to the fixed bias mechanism. By placing RE or the emitter resistance, so we can basically introduce a kind of feedback system to the transistor circuit. So similarly for the other case, so we can have this collector feedback mechanism. Collector feedback bias. So in this mechanism, so in this biasing configuration, so we have a kind of a resistor which basically connect the collector and the base. So this is your collector, so this is your collector, and this is your base. So we basically connect the collector and base through this RF or the feedback resistor. So again, if you apply Kirchhoff voltage law for these two circuit, so let's consider this input circuit. So if you apply Kirchhoff law, this is the input circuit. So then we have IC, RC plus, so this is your IB, RF plus VBE plus IE, RE equals VCC. Similarly, for the output circuit, so we can derive an equation ICRC plus, this is not IC actually, so this is IB, so this is IB, so this is IC, so then the current flow through the collector resistor is IE. So if you apply Kirchhoff current law for this node, so you can simply see that IC dash equals IC plus IB. So this is actually IE. So then the current flow through the RC resistor is ideally the it's basically equals to the emitter current. So then IERC plus VCE plus IERE equals to VCC. So then simply you can identify here RF is there. So this RF is actually connecting the collector voltage. So it's basically connect the collector voltage VC and VB. So there's a relationship between VB and VC through this RF. So for example, if the base current is changing, so then it basically affects to the both voltages, VC and VB. So this through RF, through this feedback resistor, which basically connects to the collector and base. So this RF resistor can inform whatever the variations appear in the collector, because it's basically directly connected to the base. So if you see a kind of a fluctuation appear here, so then it basically inform to this one, because this is a resistor. So if the voltage is increasing without changing the current, then definitely the base voltage should be increased to maintain a fixed voltage across this RF. Likewise, so whatever the changes appear in the collector can be simply transformed into base through this RF resistor. So this is again a kind of a stable feedback mechanism, and we can use this collective feedback mechanism commonly to our biasing circuits. So then by applying this Kirchhoff voltage law, Kirchhoff current laws for the input and output circuit, you can build couple of relationships, and based on those relationships you can evaluate the set of resistors. So if these resistors are given, you can basically evaluate the biasing currents and voltages. So the last would be the kind of a voltage divider mechanism. So the last model would be voltage divider. Divider bias. So then the circuit is something like that. So with this R1 and R2, you can basically manage your base current. So this R1 and R2 is act as a kind of a voltage divider to the base. So then through this dividing mechanism, you can basically manage the base current. Okay, so here you can find this couple of analysis there. So you can either analyze this by assuming that base current is so one mode is like, you can assume that base current is very small. So this base current is pretty much equals to 0. It's very small. So then assume that there won't be any current flow through the base. So then you can treat these two resistors separately. So it's something like that. So this is VCC, so this is R1, this is R2, and this is your base. So you can easily calculate the base voltage here. So the VB is actually VCC R2 divided by R1 plus R2. So this is because of this assumption. So if you basically absorb certain amount of current through this base, so you cannot directly apply the voltage divider rule, but for the simplicity, so with that approximation of base current equals to 0, so you can simply reduce the circuit to this model. So then the circuit would be something like that. So your input is something like that. Here you can place a kind of a so this is equals to R2 divided by R1 plus R2 into VCC. So then you can treat this as the input circuit and this as the output circuit. So you can refer the slides, then you can easily recognize that how do we apply Kirchhoff voltage law for this input and output circuit and get some equations. So through these equations, you can basically solve the circuit. So then second would be the exact way of analyzing this one. If there's a base current flow into the node, so if this IB is not equals to 0, so if this IB is not equals to 0, what we can simply do is, if IB is not equals to 0, so then you can basically remove the rest of the circuit from this divider and apply Thevenin theorem. Apply Thevenin theorem and replace this voltage divider model with an equivalent voltage source and a series resistor. So this is RTH, Thevenin resistance, and this is VTH. So how do you get the VTH? So you can just apply the voltage divider rule. VTH equals to R2 divided by R1 and R2 into VCC, because we just open it up from this one, from here and here. So then there won't be any current flow to this branch. So you can simply apply the divider here. So this is R1 and this is R2 and this is VCC. So you can just apply the divider rule here and get the Thevenin equivalent voltage. So if you want to get the Thevenin equivalent resistance, so what we can simply do is we can replace the supply with a 0 volt. So then it means like this, basically this node also grounded here. So then the equivalent resistance would be R1 parallel combination of R2. So once you set the supply voltage to 0 to get the Thevenin equivalent resistance, so you can basically have the parallel combination of R1, R2. So then this is the Thevenin resistance and this is the Thevenin voltage. So what we can simply do then is, in addition to this divider block, you can replace it with this. So then if you think of the same here, so you have resistor here. So then yes, original circuit is simplifies to this model. This model. So you have a VTH here and you have RTH here. So then you can basically apply Kirchhoff voltage for the input and output circuit with this replacement or the simplification. So then you can basically analyze the circuit and find out what are the required resistors. So what would be the currents and voltage flow through these different parts and terminals. So this is actually the simple summary of this different type of approaches. So you can basically use these 4 types of mechanism to bias the transistor. So either you can use the fixed bias or emitter biased, or this collector feedback bias, or this voltage divider bias. So the first one is very simple way of biasing, and it, so that configuration is mostly common in this switching circuit, but the rest of the 3 configuration basically we use to design these amplifiers. So then depending on the requirement and the easiness, you can stick into whatever the biasing circuit, and based on this biasing circuit you can evaluate the DC load lines, and by placing the DC load line on top of this device characteristics, you can select the Q point and what the rest of the Q point parameters like IBQ, base current, collector emitter junction voltage at this Q point. And by substituting these values to the Kirchhoff uh, load driven equations, you basically get it from this input and output circuit. You can simply calculate the corresponding resistors, or else if you are given those resistors, you can simply back calculate or calculate the currents and voltages of the circuit. So this is the entire process is called this DC biasing. So how do you do the DC biasing? First, stick into a kind of biasing circuit. So then you can select the transistor and accordingly select the data sheet and select the relevant parameters like supply voltage and the operating regions. So then according to the circuit configuration, you can basically derive the DC load line and overlay this DC load line on top of this device characteristics. So then based on the real requirement, you can decide whether you can place the Q point to the in the middle of the DC load line, or if you want it, you can place close to saturation and cut off. Because for example, if you stick into this model, if you place your Q point at the middle of the load line, so you have even I mean, like, you have a equal freedom to move it to the positive or negative direction. So because your span is simply equal. So the negative span is from the saturation collector emitter junction voltage to VCC by 2, and the positive span would be VCC by 2 to VCC. So this ultimately will ended up with a very equal span for the positive and negative direction. But what happens with that biasing is like you can basically limit it to a certain set of input signals. So you cannot basically amplify certain signals which basically have go beyond that uh, limits. For example, so if your span is between 0 and VCC by 2 and VCC by 2 to VCC, so we know that. So there's a kind of current. So if this is the case, so this is the middle, this is VCC by 2, this is VCC, this is 0. So then basically what happens, if you place the Q point here, so this is the maximum span of the input. So this is the maximum span of the input. So for certain scenarios, this span of this input is not sufficient to manage. For example, so you may ended up with this power amplifiers. Power amplifiers. So in these power amplifiers, your input is reasonably high. So with this transistor, with this single transistor, you cannot basically manage this much of amplification. Because for this particular discussion, we decided to place the Q point in the middle of the load line. So then the swing to the positive and negative directions are pretty much equal, and the base current, the swing of the base current, the swing of the base current is basically limited to this values, this band. So if you want to amplify a input signal which is basically greater than that one, so definitely if you bias the transistor like this, definitely your output would be clipped on both positive and negative directions, and you will ended up with a kind of a distorted signal like this. Okay, so it may be IC or VC, so basically distorted in these positives and negatives, because if you input a kind of base current like this, having a higher span with respect to the given spec, so then once you move it, the Q point to here, it basically jumps to saturation. And if you input this kind of external input, external base current, so then definitely it jumps to the cutoff. So then what happens is your ultimate output would be a kind of a distorted one, having this positive and negative clipped signal. So what we can do here is, so we can use the similar type of transistors. And so for the first transistor, so this is your input. Let's assume this is your input, and So this is your positive cycle and this is your negative cycle. So we will place one transistor, the Q point of the first transistor, close to cutoff, and apply this positive cycle on. So we are not taking any information from the negative cycle. We just focus the positive cycle and apply that positive cycle to one transistor Q1, which is biased close to the cutoff. So then we'll put the negative cycle. So we'll put the negative cycle to another transistor which is biased near to saturation. So then it basically can manage this much of swing in the negative direction. And if your first transistor can manage this much of input when you apply a positive cycle. So with that, two transistors, one is basically place the Q point close to cutoff, and the other one basically keep the Q point close to saturation. So then this first transistor, which is close to the cutoff, basically manage or amplify the positive cycle, and the transistor which is basically placed in close to the saturation region manage the negative cycle of the sinusoidal signal. So then we basically combine these two cycles together and have a kind of a big amplification. So this basically amplify the positive cycle, and this basically amplify the negative cycle, and if you then sum it up or superimpose it, so you will have a kind of a pure undistorted highly amplified signal at the output. So this is the concept we used in this power amplifiers. So we have two transistors basically catering or amplifying the positive cycle and negative cycle separately by placing their Q points close to cutoff and saturation. So this is one way of improving our amplification by using dual transistors or two arms. So we basically have two arms. One arm is focusing on this positive cycle, the other arm is basically focusing on negative cycle. So this once you get these amplified signals and the output of these two transistors, we basically can combine these two signals and get a heavily amplified output. So this is the concept in the power amplifiers. So what I want to highlight is this set of points. So believing that you have a kind of idea about this DC biasing and how do you manage these different type of circuits, how do you calculate the resistors we place in different branches, how do we calculate the currents and voltages flow in different elements and branches based on the given information. And believing that you have a kind of a simple idea about the operation of the transistor, what happens if we input a kind of this much of signal, whether it's clipped from the positive cycle, whether it's clipped from the negative cycle, whether it's clipped on both cycles, why this distortion happens. So then once you get that idea, you can easily design a transistor amplifier, because you know that if you basically set up or finalize the Q point and place these resistors and capacitors in the circuit, and if you plug the input and once you get a kind of a distorted output, you know that. So whether you have to move your Q point to the cutoff direction or saturation direction, depending on the a cycle, half cycle which that clipping is happened. So likewise, you can have a kind of a broader picture about this operation of these transistors in the especially in active region, and see like we can do something analytically, and through this analysis you can give a kind of a hint about the operation of the transistor with these parameters, whether this kind of input can be managed or not. So do we need a kind of a separate solution, or can we manage with the given transistor, or do we need to go for a different transistor? Do we need to adjust these resistors and supply voltages, or do we need to fine tune the Q point by shifting the load line in a different phase? So this kind of a discussion can be made with this simple concepts. So the next video would be basically covering the AC equivalent circuit of the transistor, because we know from the beginning these transistors are act as amplifiers in most of the cases. So this amplification is basically for the external time varying signal. So then in addition to this DC component quantities, so this transistor is basically work against this AC signals as well. So then the behavior of the transistor is completely different for these AC signals. And so the next would be the we can model the transistor in this AC domains and see whether we can do some analysis with this AC equivalent models. So the ultimate objective of this next would be like so we can propose a model to a transistor replaced in kind of AC domain. So if you are dealing with this time varying signals, what would be the real behavior the transistor? Now this is basically focused on DC quantities. So we found that this is the transistor. We can simply replace this transistor with this dual diode model. Once we move to the AC signal, so this transistor is no longer be a kind of a dual diode model. It has a different set of features, different type of a interpretation of this transistor. So then we can understand this model of this transistor which is in this AC domain, and see this we can do a kind of a simple analysis about the voltage gains, impedances which happen in the circuit when we feed a kind of a high frequency or low frequency signal. So we'll keep that discussion to the next session, and we'll stop it for today. Thank you.